This video presents findings from a 2-year study which evaluated sub-micron powdered activated carbon and ceramic membrane filtration to remove PFAS compounds from contaminated groundwater. The project team included members from Arcadis, the Colorado School of Mines, and Aqua Aerobic Systems in support of an ESTCP proposal for contaminated groundwater management. The primary objective was to validate the technology's ability to reduce broad-spectrum PFAS chemicals with specific focus on short-chained compounds that may have future regulatory implications. This project investigated key design parameters, methods for waste minimization, the impact of co-contaminants, and cost benchmarking to existing technologies. The technology's success is due in part to the use of a specially designed microadsorbent called Sub-Micron Powdered Activated Carbon, or SPAC. The SPAC is held in a reactor as a concentrated slurry that can range from 500 to over 50,000 milligrams per liter. The exceptionally small particle size provides more effective use of surface area and promotes greater diffusion into the pore structure. Unlike GAC or ion exchange resins, the active slurry promotes contact between the contaminants and the sorbent material to improve adsorption kinetics. The SPAC is retained in the system using a ceramic membrane, which is rated at a nominal 0.1 micron pore size. The membrane rejects the SPAC and influent suspended solids to produce a high-quality, particulate-free effluent. A cross-flow hydraulic path circulates SPAC through the reactor and membrane device to promote mixing and rapid PFAS absorption. The technology was first demonstrated at the Horsham Air Guard Station in Horsham, Pennsylvania. A dual-train pilot system was deployed near outfall number 9 in the vicinity of the existing treatment system. A series of 13 tests were conducted over 9 months and evaluated 26 separate conditions, with the final 6 tests reflecting practical design considerations. A 40 nanogram per liter effluent target for combined UCMR3 compounds was selected in anticipation of potential future maximum contaminant levels. The Horsham facility's stormwater outfall presented challenges with variable sediment loadings caused by precipitation and wind events. The use of a 5-micron cloth media filter provided effective pre-treatment for sediment removal without affecting raw PFAS values. With the pre-treatment system in place, the pilot system successfully demonstrated compliance with the effluent target from an influent over 5,000 nanograms per liter using 2-stage treatment. The SPAC achieved nearly complete removal of PFOA and PFOS and greater than 90% removal of the 4 carbon-chained PFBS. Effective treatment was achieved at SPAC concentrations from 10 to 40 grams per liter with as little as 5 minutes of reaction. Rapid, small-scale column tests were conducted using GAC on the same water source to compare its adsorptive capacity with SPAC. As GAC was unable to meet the 40 nanogram per liter effluent target, the breakthrough threshold was set to 10% of the raw PFAS concentration. In this comparison, the SPAC adsorbed about 300 to 700 times more PFAS than did the granular activated carbon. The pilot system was then moved to the nearby Willow Grove Naval Air Station to treat groundwater that contained significantly higher PFAS levels. A series of 5 tests, each with 2 conditions, were conducted using the 2-stage pilot. Unlike the prior surface water application, the groundwater characteristics were stable and contained little or no suspended solids or TOC. Testing further confirmed that the SPAC and ceramic membrane technology was able to meet the effluent target from an influent exceeding 40,000 nanograms per liter of combined UCMR3 compounds. The system also achieved PFBS reductions from 700 to less than 18 nanograms per liter in the dual-stage arrangement. Another project objective was to identify methods to minimize waste production. Testing evaluated the final SPAC volume after concentrating with the membrane and gravity settling batch settler. Results showed the system successfully concentrated the spent SPAC to 144 grams per liter within about 10 minutes using membrane filtration. Once removed, the SPAC was further concentrated to nearly 250 grams per liter within a 16 to 24-hour period. Results from the waste minimization testing suggest final waste volumes from 20 to 80 gallons of waste produced per 1 million gallons of water treated. Life cycle cost analyses were performed using the results from both the Horsham and Willow Grove applications. In the Horsham Air Guide Station evaluation, a 100-gallon per minute design flow produced higher capital costs for the SPAC and ceramic membrane system, but its operational savings resulted in an 8-month payback period over GAC. A 20-gallon per minute design flow for the Willow Grove application showed that both capital and operational costs were similar for the S-Pack and ceramic membrane filter when compared with the best-performing single-use ion exchange resin. Sensitivity analyses suggested the S-Pack and ceramic membrane filter costs were less reactive to adverse design factors such as increased PFAS species present and the presence of co-contaminants. As health and environmental concerns continue to drive regulatory pressures, military services will need access to a selection of proven and resilient technologies to enhance performance, reduce costs, and deliver sustainable results. This ESTCP project effectively demonstrated how a unique arrangement of S-Pack and ceramic membrane technologies can deliver a cost-effective and reliable option for contaminated groundwater and surface water applications, and should be included in side-by-side testing when evaluating other treatment alternatives like granular activated carbon and ion exchange.